All right, let's take a look at some limits of infinity. Man, that'd be a great band name, wouldn't it? Limits of infinity. Anyway, what I'm talking about is we want to figure out when a limit will have a value of infinity instead of an actual number. I also want to take some time to divide polynomials. Here's a limit that we should be fairly comfortable with. The limit as x approaches 5 of 1 over x minus 5. Now, if we were to use a sine chart here, we'd identify that most important point being 5, because it makes the denominator 0, not the whole function. When the denominator is 0, then we're going to have a vertical asymptote. So we test each interval, picking a value to the left of 5, like 0, 1 over 0 minus 5. 1 is always positive, but 0 minus 5 would be negative, making the entire fraction negative. As we pass over 5, x minus 5 becomes positive, and the entire fraction is positive. Now when we want to graph it, we see that the degree of the numerator is smaller than the degree of the denominator, so we have a horizontal asymptote at the x-axis. Now we got everything we need to come up with a sketch of a graph. In the first interval, since it's negative, our graph has to be below the x-axis and approach both of our asymptotes. On the right side, it's going to be positive, so above the x-axis, but still approaching both asymptotes. Now, when we want to determine the limit as x approaches 5, we notice that if I come at 5 from the left, I'm expecting it to be negative infinity. Coming at it from the right, we expect it to be positive infinity. Because those two expectations are different, that's why this limit does not exist. Now, if we are anywhere else on this curve and we want to find the limit, say, as x approaches 0 of 1 over x minus 5, well, every other part of this curve is continuous. So when we're over here at x equals 0 and we want to check out the limit, well, coming at this point from both sides would give us the same value, and that would be what we get when we substitute 0 in for x. So that limit is going to be negative 1/5. But how did things change when we have that double root in the denominator, when we have that factor that's being squared? If we take a look at the sine chart, we still have our most important point is at 5. Makes the denominator 0 so that we still have a vertical asymptote there. The degree of the numerator is still smaller than the degree of the denominator, so we still have a horizontal asymptote as the x-axis. But now when we go through testing some points, if I pick something smaller than 5, like 0, 1 is going to always be positive. 0 minus 5 is negative, but we're squaring it. So this thing will always be positive. As we pass over 5, then the factor x minus 5 becomes positive, but we're squaring it, so it stays positive. And so we have a sine chart that looks like it's positive everywhere that the function is defined. And now when we graph it, that first interval being positive now is going to be above the x-axis, but still holding close to both asymptotes. Same thing on the right side. Positive and holding close to both asymptotes. And when we want to evaluate the limit, just because there's an asymptote there doesn't mean that we're going to have a limit that does not exist. Now, as I approach 5 from the left, this function is going to grow. And as I approach it from the right, it's going to grow just as fast in the same direction. So that both of those expectations are that this function is going to keep going up and up and up forever. And so this is how we get a limit of infinity. So it's looking like squares are what are going to give us limits of infinity. So let's take a look at a function that's got a couple of squares in it. 2x squared over x plus 6 squared. If we're going to take a look at its sine chart, we have two most important numbers now. One of them is 0, and the other one's going to be negative 6. Negative 6 is important because it makes the denominator equal to 0. So we're going to have a vertical asymptote there. And 0 is important because it makes the numerator 0, so the entire fraction would be 0. Now as we go through testing each interval, picking something very negative, like negative a billion, all right? 2 is always positive. Anything squared is always positive. And in the denominator, anything squared is always positive. So that means on this interval will be positive. As I pass over negative 6, it's x plus 6 that changes to positive, but we're squaring it, so our sign stays the same. And as I pass over 0, it's x that turns from negative to positive, but we squared it, so it's always positive. And we have this function that's always going to be positive. Another thing to note is that when we're looking at a horizontal asymptote, since the degree of the numerator and the degree of the denominator are the same, all we have to do is take the leading terms and simplify them. So we'll have 2x squared in the numerator and a single x squared in the denominator. That's going to give us a horizontal asymptote at y equals 2x squared over x squared, which is just 2. So we have this horizontal asymptote at 2. Right. So what's this thing going to look like? On the first interval, since we have to be positive, we have to be above the x-axis. We're also actually going to be above the asymptote and holding close to both of them. On the next interval, between negative 6 and 0, we have to start with this vertical asymptote. But we do have to get down to the 0, so we are going to cross that asymptote to get down to our 0. Which is okay, all right? Because asymptotes have nothing to do with the middle of the graph, only the extremes of the graph. So as we go further beyond 0, this is going to be positive as well, so our curve is going to stay above the x-axis, but now we have to approach that asymptote. So this is actually what our graph is going to look like. Now, when we want to determine our limits, the limit as x approaches 0, this is where 0 is, and whether I approach it from the left or the right side, my expectation is that the value is going to be 0. So that limit is 0. At negative 6, however, because whether we're coming at it from the left or the right, this function is growing without bound. It's going up all the way. That's going to have a limit of infinity. So it looks like squaring is important, that when we are squaring, that's when we're going to get a limit that has a value of infinity. But it's the squaring has to happen in the denominator. That's where we'll get our limit of infinity. So let's take a look at one that's a little bit more complicated. The limit as x approaches negative 2 of 2x times x minus 3 over x plus 2 times x minus 1 squared. All right, first, we could probably guess and be accurate as to what this limit is going to be. We're looking at the limit as x approaches negative 2. We know that that negative 2 is coming from this factor. That factor is in the denominator, so it'll give us an asymptote there, and it's not being squared. So I would anticipate that the limit from the left and the right are different, so we should expect our limit to not exist. But let's go through it to verify. When we're creating our sign chart, from the numerator, I see we have two important numbers, 0 and 3. Since they're in the numerator, they're going to make the fraction equal to 0. In the denominator, we have two important numbers of negative 2 and positive 1. Those are both in the denominator, so they'll give us asymptotes. As we test each interval, picking a number that is smaller than negative 2, like negative 1 billion, 2 will always be positive, but x being negative 1 billion will be negative. X minus 3, negative 1 billion minus 3 is negative. Negative 1 billion plus 2, negative. Negative 1 billion minus 1, negative. However, this one is being squared, so this will always be positive. As I count, looks like I got 1, 2, 3 negatives, so the entire fraction will be negative. Then quickly, as I pass over negative 2, it's the factor of x plus 2 that changes to positive. Now we have an even number of negatives, so the fraction is positive. As I pass over 0, it is x that changes from negative to positive. Now there's only one negative, so the entire fraction is negative. As I pass over 1, it is x minus 1 that changes to positive. However, that was always being squared. It's always positive. We haven't changed the number of negatives in our fraction, so the value stays the same. Then, as we pass over 3, it is x minus 3 that changes value. And all those positives means the fraction is positive. Now we have enough to come up with a really good sketch. As we're checking degrees in the numerator, I have an x times an x. That'll leave me with an x squared. In the denominator, we have x times x squared, which is x cubed. Since the degree of the numerator is smaller than the degree of the denominator, we have this horizontal asymptote on the x-axis. Now we're ready to graph on that first interval. Since it's negative, we'll be below the x-axis, and we need to hang close to both of our asymptotes. From negative 2 to 0, we're positive above the x-axis, so we're going to start being close to our asymptote, and we need to get over to the 0. So we're going to look like that. Between 0 and 1, it's negative. We need to go through that 0 and get close to our asymptote. From 1 to 3, we're staying negative. So we're starting close to our asymptote and getting over to this 0. And after 3, it's going to be positive. But we do have this horizontal asymptote, so eventually it's got to come back down and get close to that asymptote. Now to evaluate our limit as x approaches negative 2. As we approach it from the left, we expect negative infinity, and from the right, we expect positive infinity. So our guess was right that this limit does not exist for the reasons that we thought. And if we try and find that limit as x approaches 0, well, we have no worries about 0 because 0 came from a factor in the numerator. So we're not going to have any asymptotes there. There's no big disconnects or anything. So our limit is going to be that value at 0, which is 0. Now, as we look at the limit as x approaches 1, this is an important point to make. We're going for x approaching 1, and that comes from this factor, which is squared and in the denominator. So we would expect an asymptote, but both sides approaching the same thing. So our initial guess would probably be that it would be infinity, that the value of the limit is infinity. However, when we look at the graph, if we approach 1 from the left or the right, what we were anticipating did actually happen. We do have an asymptote there. And because it's squared, both sides do go in the same direction, but they're both going down, not up. And so there is still an importance to coming up with the Sine Chart at the very least, so we can visualize the graph and recognize that this is going to go down forever, so our limit is actually equal to negative infinity. One more little warning here. Let's take a look at the limit as x approaches 4 of x minus 4 squared times x plus 2 over negative 3 times x minus 4 squared. And as we're looking at our limit, x is approaching 4, which comes from this factor, or this factor, actually. So are we dealing with this being a 0 or with this being an asymptote? Right? And in actuality, algebraically, both of those factors are going to cancel, which means that as a limit, this limit is the same value as the limit as x approaches 4 of x plus 2 over negative 3. And since 4 is not a part of either of those factors, we could just substitute 4 plus 2 over negative 3. 6 over negative 3 is negative 2. Right? Now, as we look at that on a Sine chart, we have important numbers at negative 2 and at 4. At negative 2, we definitely have a 0. Because x minus 4 is in the numerator, that means that 4 will make our numerator equal 0, but because it's also in the denominator, it'll make it undefined. So it's definitely, 4 is not a part of the domain. Right? If we look at the graph, or we look at the signs as we go through, the sign, pick a number smaller than negative 2, like negative a billion, everything that's squared is going to be positive, always. But negative 1 billion minus 2 is negative. Negative 3 is always negative. So this part of the function will be positive. After that, x plus 2 changes to positive, so now we're at a negative. And as we pass over 4, nothing else changes, so we're still negative. And we get a line, essentially we get the line negative 1/3 x minus 2/3. So a line that looks like this. And what's happening at 4 is actually that we have a hole. So whether we approach 4 from the left or the right, we still are going to expect this value, the value being negative 2, even though negative 2 isn't a part of the range. There's actually a hole there. There's no value at that spot, but our expectation is negative 2. If you need to pause and take a break, now would be a good time before we get into division. But just as a reminder, when it comes to synthetic division, the process of how we do it, we first lay out the coefficients of our numerator. So that would be 1, 8, and 1. And this little box over here, and we set it up with a long line, little mark at the bottom. Right? What goes in the box is actually the 0 of the denominator. So negative 4. Then bring down the 1, and we're just going to multiply and add, multiply and add, multiply and add. We're always multiplying by what's in the box, the negative 4. So 1 times negative 4 is negative 4. Then as we move down, we add these two together, multiply by the negative 4, add those two together, we're at negative 15. And what that tells us is that we can rewrite this fraction as 1x plus 4, and what's in the box is our remainder. So we would have negative 15 over x plus 4. Now, as that division gets more complicated, we try and do the same thing, where we're going to lay out all of our coefficients of the numerator, which we have 1x to the 5th, 1x to the 4th. Since there are no x to the 3rd terms, we do have to use a 0 there. Negative 3x squared, 5x, and a negative 4. So we'd put our long line here, here's our remainder, and we need a box. The problem is, when we look at the denominator, we don't have any linear factors. So we can't put anything in the box, and synthetic division isn't going to work here. And that's why we need long division. Just to practice some long division on something a little smaller first, long division with polynomials works very much like it did with numbers. We're going to take the numerator and put it inside, so x squared plus 8x plus 1. And then we'll take the denominator and put that outside, x plus 4. And as we go through long division, we're really kind of keying off of this term right here to help us along the way. Right? And we're asking, what do I got to multiply that x by to turn it into x squared? And, well, we'll have to multiply it by x. So do that. Go back and multiply the entire x plus 4 by x. And we'll get x squared plus 4x. Once we have that, we're going to subtract the entire thing. X squared minus x squared cancel. 8x minus plus 4 is 4x. Then we bring down the 1 and do it all again. Keying off of that x, what do I got to multiply x by to turn it into 4x? And that would be by 4. So multiply the entire x plus 4 by that 4. And we'll have 4x plus 16. When I subtract the entire thing, 4x's cancel. 1 minus 16 is negative 15. Since there's nothing left, that's our remainder. How do we write a remainder? As a fraction. Negative 15 over x plus 4. So we do get that same answer using long division. When we had this big ugly fraction where our denominator couldn't be written with linear coefficients, then we have to use long division. as we set it up, the numerator goes inside. We'll have x to the fifth plus x to the fourth plus 0x to the thirds minus 3x squared plus 5x minus 4. And on the outside, we'll have x squared minus x plus 1. And it looks like I need a little more room here. Now, as we go through our long division, remember we're going to key off of this x squared. Right? What do I have to multiply x squared by to turn it into x to the fifth? And that would be x to the third. So do that to the entire quadratic here. And we'll have x to the fifth minus x to the fourth plus 1x to the third. And subtract all of that off. The x to the fifths are going to cancel. Don't be fooled. X to the fourths do not cancel. We got x to the fourth minus a negative x to the fourth. So it'd be 2x to the fourth. And 0 minus x to the third is a negative x to the third. And we bring down the negative 3x squared and do it all again. What do I got to multiply x squared by to turn it into 2x to the fourth? That would be 2x squared. That would give me 2x to the fourth. Multiply it by negative x, and we'll have negative 2x to the third. And multiply it by 1, and we'll have plus 2x squared. Subtract every term. Negative 1 minus negative 2 is positive 1x cubed. Negative 3 minus 2 is negative 5x squared. Bring down the next term, the 5x, and do it again. What do I got to multiply x squared by to turn it into x to the third? That would be x. When we multiply the entire quadratic by x, we get x to the third minus x squared plus x. Subtract all of that. 5 minus negative 1 is negative 4x squared. 5 minus x is plus 4x. And bring down the minus 4. Do it one more time. X squared to turn into negative 4x squared would be minus 4. Negative 4x squared. Negative x times negative 4 is positive 4x. And negative 4 times 1 is negative 4. This is awesome because now when we subtract negative minus negative, those cancel. 4 minus 4, those cancel. Negative 4 minus negative 4, those cancel. And we have no remainder. Right, so just some practice in using synthetic and long division. We're going to need that pretty soon.